Hello folks, welcome back to Merrill Math. I'm Mr. Merrill, and today we're going to talk about just one example finding a derivative using the chain rule. Now this is I would probably say a Calc 1, or I guess Calc AB, I guess is what they're calling it now. Maybe BC. They talk about chain rule in both of them. There's a lot of overlap between the two classes. But a derivative using chain rule, we're going to the extreme on this one. So this is the first calc topic I think I've covered on this channel. But this one, I came across it a while back, and I thought it was an interesting problem, so we'll take a look at it. So the chain rule, when you're taking derivatives, is basically saying, like, there are things that you have to unpack. So when you're taking like the derivative of like sine squared x, or like e to the x squared, or things like that, or even just the derivative of x squared, I guess that would be a power rule. Never mind. So chain rule is when there are things that you kind of have to unpack as you're working through this. So this, we can tell there are a lot of things going on here. So what we're going to, sort of our strategy for tackling this, for this derivative, is we have to think about a lot of different things. So we're going to work our way from the outside basically to the inside. So we're going to start with tangent, and then we're going to work our way to the e part, and then we're going to work our way to the x squared part. So there's a whole bunch of stuff to take a look at here. So where we're going to start is this tangent cubed. So if I take the derivative of tangent cubed of something, I can think about this as like a power rule situation. So the 3 will come out front, 3, and the power will decrease by 1, so tangent squared. And this part is going to stay the same in that case. And then I have to think about this. So tangent e to the x squared, and I have to think about the derivative of this piece. So that's our first chain rule part. So this here is just power rule. This is our first chain rule part. So we have to find the derivative of that. Well, the derivative of tangent is secant squared. So this part, we've got 3 tangent squared e to the x squared, and derivative of tangent is going to be secant squared e to the x squared. But we took the derivative of this, and now we have to take the derivative of the inside piece. So this e to the x squared, now we have to think about the derivative of that. So this is our second chain rule application. So now we've got 3 tangent squared e to the x squared secant squared e to the x squared, and then we're taking the derivative of this. So the derivative of e to the x squared, well, the derivative of e to the whatever is just e to the whatever. It doesn't change. This is one of those interesting functions that is the derivative of itself. So that's kind of nice. So I've got e to the x squared. Now I have to think about the derivative of this piece. Well, the derivative of x squared is, well, that's going to be 2x. So that would have been the chain rule part there, but derivative of x squared, if you're doing a problem like this, you should know what the derivative of x squared is. It's 2x. So this is our answer. So we can do a little bit of cleaning up here and just kind of combine some terms and move some things around so it looks a little bit prettier. So what we've got is 6. How do we want to do this? Let's say x, and we'll do e to the x squared, and then we'll go tangent squared e to the x squared secant squared e to the x squared. And that is our derivative. So this is a, I guess, quick video on a derivative using the chain rule to the extreme. If you have any questions or comments, be sure to leave those in the comment section below. Otherwise, thanks for watching.